Okay, in the last unit, we did backpropagation for programs with scalar values. Now we want to consider programs, high-level deep networks, built out of tensors and arrays and vectors. This is what typical networks really emphasize. Okay, so here's a multi-layer perceptron. Multi-layer perceptron is written in terms of vectors and matrices. So this is a two-layer perceptron. We're going to be focusing on computing the gradient of the loss function, the ultimate loss function, with respect to the model parameters. And that's going to support stochastic gradient descent. So let's think about what that gradient is. So if I take the gradient of the loss with respect to this matrix, say, what I'm really interested in is the partial derivative of the loss with respect to each particular number in this matrix. So that system of partial derivatives has the same number of numbers as the matrix. So in terms of tensors and arrays, what that means is that the gradient is also an array or a tensor with the same shape as the thing that it's a gradient of. So just like the scalar case, we're going to be dealing with objects that have a value attribute and a gradient attribute. And in the case of a matrix, the value and the gradient have the same shape, and that will generalize to tensors. Source code loops. So if you take a course or read a textbook from some other source, when they do the general case of matrices and tensors, they'll often talk about Jacobian matrices. So if I have a general mapping from vectors to vectors, the derivative of that mapping is a matrix, the Jacobian matrix. However, in deep learning, we're dealing with, almost always, we're dealing with a special case where we're simply multiplying matrices and vectors or some kind of multiplicative contraction. So in that case, there's a much simpler way to understand the backpropagation for the array and tensor case. So I want to consider one of the lines in our program. So this is the line in the program that computes the score from the hidden layer. So the hidden layer is a vector. We're going to multiply it by a matrix to get a new vector, the vector equal to the number of possible labels. We're going to compare that to a threshold, pass that through an activation function to get a score. So the first thing I'm going to do is write out this matrix multiplication in terms of a loop. So that matrix multiplication can be written by taking an intermediate variable representing the matrix multiplication, which I'm going to call S tilde. I initialize that to 0, and then for each value of j, I loop over the values of I, computing this product and adding them together to get a sum over I in S tilde j. And this loop is just the implementation of the matrix multiplication. This is what the matrix multiplication is. But now what I've done is written that matrix multiplication as a loop over program steps that are completely scalar to scalar, right? This is looking at one particular entry of that matrix, one particular entry in the vector, and adding it into one particular entry in this intermediate variable, S tilde. And the last step of applying the activation function to each element of this vector can also be written as a loop, right? For each j, we set the sj to be the result of taking our matrix multiplication result, comparing it to a threshold, passing it through the nonlinearity to get our score for j. Okay, so let's do backpropagation on these loops. So let's look first at this simple loop, right? So backpropagation is running backwards, right? So you start with the loss and you're computing the gradient with respect to various variables backward through the program. So the first thing I'm going to assume that coming backward through the program, I already have the gradient of the loss with respect to this score. And I'm going backward and taking the gradient of the loss with respect to this score and computing gradients for S tilde and for B. And what I'm going to do is just take this scalar assignment for each value of J and do that backpropagation for that scalar assignment, right? So it's just the chain rule. So the derivative with respect to S tilde is just the derivative of the loss with respect to S times the derivative of S with respect to S tilde. So it's the derivative of the loss with respect to S, that's S dot grad of J, now we're working with a particular J, times the derivative of the activation function at the point we're talking about. And the same thing, exactly the same calculation holds for taking the gradient of the loss with respect to B. B occurs negatively in here, so the gradient is flips, and we represent that by a minus equal here. And now we're going backwards, so we just computed the gradient with respect to S tilde going backwards. So now we want to take the gradient with respect to S tilde and get a gradient with respect to W and a gradient with respect to H. Right, so we're going backward through the program. But again, we just take this loop and we just treat the body of this loop for each particular value of J and I, and we do the gradient backpropagation for that particular loop instance. And for that particular loop instance, we just have scalars. So to get the W dot grad of Ji, it's the same shape as W, we take the gradient with respect to S tilde times the effect that a change in W has on S tilde, which is just H of I. And a very similar calculation gives the gradient, that should be an H, gives the gradient with respect to H. And this approach of representing tensor products as loops is completely general. So I can take a very high dimensional tensor. So just in case, just to review, a tensor is just an array with more than two indices, with possibly more than two indices. So I can take this is a third order tensor. It has 3 indices. And here I've written a contraction between 2 third order tensors to define this tensor. But I can write that as a loop, and then to do the backpropagation, it's essentially the same thing I just did, but it applies now to these loop bodies, which have many more indices. But each particular example of this loop body is just a scalar operation that you can compute the backpropagation of in a sort of trivial way. So that's a very simple way, I think, of looking at or handling backpropagation over arrays and tensors. Thank you.